Hi, everyone. Thank you for that warm welcome, Dr. Franz. So nice to meet you all. My introduction has been done already. I work in AI machine learning for pharmaceutical in Microsoft UK for about 4 years now. And when I joined Microsoft, I joined the Quantum Ambassador group as well. I've always been passionate about physics. In fact, all the sciences. I love all the sciences, especially modern physics. So quantum computing naturally was fascinating for me, and I was studying it before joining Microsoft as well. So I joined the ambassadors team. So it's my day job is majorly AI, machine learning, generative AI, and all of that, and I do quantum as well on the side, and it kind of works out quite nicely for the industry I work in because that is the industry which is first application for quantum as well, which is pharmaceutical and life sciences. I've also done 5 years of STEM teaching quite early on in my career, and I used to love teaching. I still like teaching. I'm very close to academia, and I love kind of being going into academia sessions. Just last week, I was with Imperial College as well. I like meeting academia folks so that we can do more collaboration. If anyone is interested, please reach out to me on LinkedIn. Now that's about me. What we are here to do is, of course, talk a bit more about quantum. I know some of you might know things that I'm already going to talk about, so I'm sorry for that, but I just want to make sure that we ground everyone at the same level, and then we can go ahead with the similar understanding actually. So I just want to make sure everybody's on the same page. Um, First couple of slides are going to be grounding, trying to understand quantum versus classical, right? And then we will get into what Microsoft is doing, and then we'll get into hardware, Myron, and etc. Basically. So with classical versus quantum, right? As we all know, like the classical computers were especially developed to automate complex arithmetic calculations accurately, and I mean, of course, which we used to do manually, right? I mean, all the work that computers do now, we used to do manually, and certain calculations take very long time, right? And that's what computers were here to do. But they do far more than that today, right? So right from data processing to running our workflows, help us to do better science. With the advent of generative AI, we have also seen that classical computers can also help us with some decision making, right? Of course, augmented with a human in the loop scenario. So classical computers are here to do a lot. But even with the power that we have with classical computers today, there are certain problems which are classically intractable. Even for the scale of supercomputers that we have, the best supercomputer that we have today, right? What are these problems? These problems are at the root of simulating natural processes like creating enzymes, catalysts, or even accurately simulating molecules and natural systems, right? Now, um, we have not been able to do that accurately with classical. I'm not saying we can't do it. We can't do it accurately with classical means, basically. One very trivial example, and I love talking about caffeine, right? It's one of the basic molecules, and it's very close to me because I drink tea like twice a day at least, and we all do. It has caffeine, and caffeine is a very basic molecule which classical computers actually face challenge simulating, right? So if you think about the picture that the classical computers paint in terms of simulation for caffeine in front of us, is very fuzzy view of caffeine as a molecule. Now, one cup of coffee has about 3 times 10 to the power of 20 caffeine molecules. We can't simulate one accurately, right? Let alone all the interactions with sugar, with milk, and with water and whatnot, the whole system as such, right? There's entropy at play, there's temperature at play, there are many other things at play, right? We can't simulate that system. But something very important as well, some humanity scale problems like food production. We have a very important process called as nitrogen fixation, which is synthetically creating fertilizers. Now it is said about 3 to 4% of world's energy is spent on just this process, right? Which is synthetically creating fertilizers. And even after that, we have challenges in terms of food production. We still, we have countries where food production is still a problem. We can't produce enough. Now, plants and nature does this very naturally. So plants produce nitrogenous, which is kind of a natural fertilizer, right? They do this quite easily and efficiently, right? We can't actually simulate that process. We can't simulate that in its complex enzyme, right? But imagine the world where we can do that. uh, how good it will be, not just for food production as a problem, but also for sustainability. We are consuming 4% of world's energy doing this, and it's going to increase, right? Because the population is increasing naturally. So, what did we understand about this process, right? These processes, which nature executes very efficiently, are at the core of quantum mechanics. So we know nature is operating at a quantum level. It computes at that level, right? And very, very efficiently. Now it is said that this process, if we have to do with the classical computers, is going to take us millions of years, and it's going to take us enormous number of bits that we don't have today, right? But if you think about quantum computers, the research says that we could crack this with few number of equivalent of bits, which is qubits, some 200, and it will take us hours or maybe days to simulate this process, right? So it would be very good if we could actually get hold of how nature does this, right? And that is very quantum mechanical at the core. And that is the reason why we can see that quantum computing can actually solve problems which are grand, which are human scale, which we are unable to tackle today. And that's why people like me, like a lot of other experts who work on quantum computing, have been invested in quantum mechanics, the research, the physics part of it, and the computing side of it for more than hundreds of years, right? This year is 100 year of quantum information science and technology, actually. So it's been a long time that we are investing into this, right? And there's a reason why we stay invested into it. And I'm very passionate about this space. Now, like I said, when I say quantum mechanical level, what does really happen? Right? It happens at a very, very microscopic level, right? At subatomic level, not even microscopic level. When I say subatomic, it happens at atom, electrons, quarks. That's the level where quantum really operates, right? Very, very small level. So we can't see it in day-to-day life. It's said that classical world is actually approximation of quantum world at that level. So we are living what we see is approximation of the reality, to be honest. Um, so this kind of gives a very good example of where. Let me just bring out my pointer quickly. Um, yeah, so this kind of, I don't know if you can see my pointer. I think it said no. Fine, that's okay. So it's at the extreme left level, right, where it happens basically. Now we know in in 17th century, right, we discovered 17th, 18th century, we just discovered that light is made up of particle. It's not just like a wave, right? The journey actually began with Sir Isaac Newton in 1670s, where he proposed the light was made out of particles. And then a lot of other research was done, like fast forward to 19th century, Thomas Young's double slit experiment in 1801 painted a very different picture of light. It said light is not just a particle, but it is also a wave. So it shows wave like interference patterns. But then we know that there is wave particle duality. That light presence, right? And then story took another turn in 1905 when Sir Albert Einstein explained the photoelectric effect, suggesting that the light also behaved as discrete particles of energy or photons, right? So the light functions as both particle and wave depending on how the experiment is conducted and who is like how the observations are made as well. So this duality kind of is foundational to the advent of quantum mechanics. And then what happened was, sorry, I double clicked. Right. And so what happened was, as you see, right, Louis de Broglie, in 1924, he did an experiment which said it's not just light that behaves like this, but it is also every particle. any particle that exists in nature actually exhibit this property at the subatomic level, that it behaves both as a wave and particle at the same time. So Louis de Broglie actually started this revolution. His hypothesis actually started the revolution of quantum theory. So that was a pivotal moment in the quantum physics era, right? So it was like spooky to know that everything actually behaves like that. And of course, he was awarded Nobel Prize for it because it was such an important, pivotal moment in the history, basically. And then, I mean, then it started, right? Then we had Niels Bohr in early 20th century talking about the Bohr's model. Then we had Heisenberg talking about uncertainty principle, saying that, at that level, you can't precisely measure position and momentum of the particle at the same time. We all have heard about Erwin Schrödinger and his cat, right? Like Schrodinger's cat is so famous. He talked about how these particles can simultaneously exhibit multiple possible states or configurations, right? The cat could be alive or dead at the same time in the box, right? So then the wave started of what came next, right? So what really makes quantum different? What is it that it is powerful enough for us to do things which we can't do today? That even with all the successful inventions we have done so far, right? What quantum brings to the table comes back from that wave particle duality, right? It brings interference to the table, which is very, very important to get the quantum parallelism power that superposition shows, right? So interference is at core of any quantum computation that you do. And superposition actually comes from it, right? So what superposition tells us is a particle can exist in multiple states simultaneously. So in context of quantum computing, this principle is actually represented with the qubits, and I will show you the qubits on the next slide. They're equivalent of bits basically, but it is represented in a way that you can have harness multiple states at the same time. And remember, this happens at a very low level, right? And that gives the quantum parallelism power, right? That we have. So multiple states at the same time, you can actually execute those multiple paths at the same time, basically. And what entanglement brings to the table is basically the correlation of these particles, right? And that correlation is so tight that it defies the locality. It goes beyond locality into non-local world, where it says, no matter where you are, where this one particle is, the other particle sent far beyond somewhere else, in another galaxy. If you measure one, you'll be able to measure the other. And this is no longer like a theory or spookiness, as Einstein said, right? This is real. 3 years ago, there was a Nobel Prize awarded to the scientists who actually proved this in the lab, right? So it's not theory, it's real. And quantum entanglement actually serves many purposes in quantum circuits, in a lot of algorithms that we see, but also in quantum communications, like in the quantum key distribution algorithm. It plays a very, very vital role. So both superposition and entanglement are at the core of quantum becoming what it is, basically. The fourth one at play is measurement. And of course, we in our world, when we think about computing, we want to measure things like in the classical world, right? So measurement actually drops the quantum state. As soon as you observe, the wave function drops, basically. And that's where it kind of gets into the classical world, and we can bring it back. We can bring the measurements back into the classical results back into the classical world. And there are a few other things like, no cloning theorem, which is also quite important aspect of quantum computing, which is you can't really, like copy the states like we do in the classical computing. The reason being, as soon as you make observation, any type of observation, right? When you copy, you observe, right? Any type of observation is going to make it drop the state and become classical, right? So you can't necessarily clone, which is also very important in the quantum communications and the quantum security domain, basically. So these are some of the fundamental principles that make quantum what it is and make it different, right? Um, but what about quantum computing? When did that happen, right? So, if you think about history, in 1981, 82 is really when quantum computing as a field began, when Sir Richard Feynman talked about harnessing these properties of quantum mechanics to create a computer that can do better or faster information processing, right? That's when the race for quantum computing actually started. So quantum theory, quantum mechanics, then we started looking at the algorithms and came, of course, the hardware and the algorithms came at that time, which is the computing era. So this is actually how it happened, right? So right from 1900s, it actually goes slightly beyond that with the light, as I said. But if we stick to 1900s, then the whole path actually you can see how the theoretical foundations were made, and then the development of the algorithms, and of course the ongoing advancements in the hardware space, where you have most of the big players and a lot of research going on, a lot of startups investing into this. So lots going on in the bottom space, in the bottom curve, because we are all racing towards building the hardware, the computer, basically. We spoke about what computer is, but like what is difference, right? So in the classical world, we see the bits, they are the basic unit of information storage and processing, whereas quantum computers use qubits, equivalent to bits, basically. Uh, a bit is deterministic, and can either be 0 or 1. And it all depends upon the voltages, right? We have worked this out. We have converted the classical world from analog to digital. So based on the voltage level below a certain range, 5 millivolts, it's 0. Above that, it's 1. So we have our own way of interpreting zeros and ones, right, in the classical world. Likewise, in the quantum computing space, a qubit can exist in multiple probabilities. So it's no longer deterministic. It is very probabilistic in nature, right? Multiple states at the same time, basically, and which comes from superposition, right? The principle that we just saw, right? Which is underground is the subatomic particle wave duality, like particle wave duality, basically. So superposition is very key element of the qubit. You put it in the state that it is super in superposition, so it can have this multiple states at the same time, and we could harness that for processing. So in the classical world, if you have 4 bits, you can harness one state out of these 16 states at one time, right? That's what you could do. But in the quantum world, because these qubits are in superposition, 0 or 1, at the same time, you can harness all 16 at the same time. So if you think about it, 4 qubits are actually equivalent to 16 bits. Um, that gives immense power, right? To the power of n, right? That gives immense processing power. So if you think about processing power, n qubits, as I said, is equivalent to 2 to the power of n bits. So about 50 qubits will give us 16 petabytes, right? That's huge. That's huge. But when we say 50 qubits, we need 50 good, beautiful, behaving qubits, right? Qubits that can actually behave and be reliable. So, which we are slightly far off from today. I'm going to move some slides ahead because I think I've explained this part. But hold on to that thought of qubits, 50 qubits, and we'll get back to it. So in the classical world, you have, like I said, 0, 1. In the quantum world, we depict this in the block sphere. It's a 3D sphere, right? A sphere is 3D, so it's called as block sphere, and you can actually envision these states on the sphere and inside the sphere. There's a concept of pure and mixed states, right? So we are not going to go into a lot of details of pure and mixed states, but it's a 3D world, right? And it is also quite embedded into the complex side of the complex number side of the mathematics. So we envision this block sphere and these states that quantum exhibit into a Hilbert space. It's a space that is actually in depicting some of the complex side of the mathematics as well. So that's where it kind of becomes kind of 3D representation. It's not 2D flat like our classical world. The way we actually, the canonical definition, as it says, of the states within quantum computing is the 0 and 1 state, and these are kets. They're called as kets, basically. So that notation that you see is ket, and the matrix notation is 1 0 and 0 1, basically. Now, when I say superposition, right, it's important to understand what happens in superposition, right? So when you look at this a wave equation, right? This, you see psi, alpha is the magnitude of ket 0, state 0. Beta is the magnitude of ket 1. The probability of seeing from the probability theory is alpha square or beta square, and together they are 1, right? It's always 1 because we normalize. We normalize the space. We want it to be normalized so that the computations become easy. So because we want it to be, normalized in state 1, basically, and that's where probability theory comes into picture as well. So alpha square plus beta square actually gives us probability 1 of the system, but when the measurement happens, depending upon which is more dominant, you will see that results, right? And when we say probability, it's not measuring once, right? It's multiple different epochs of measurements, and you kind of then look at the maximum out of that, right? There are ways to kind of do that. So probability amplitudes will give you, which state it is going to collapse into, basically, most of the times, because it is probabilistic. Now, there are multiple gates. There are multiple different gates that we operate in quantum. Like in the classical world, there's an identity gate, which kind of gives you the same state back. There are gates that change that flip, like a NOT gate, just change from 0 to 1. There are gates which are changing the phase. Now, phase is at the core of any quantum computation. We induce phase in quantum circuits because we want to harness the quantum computing power, right? Now, there are gates that can put the state um, into a phase shift, basically. I'm conscious that we haven't looked at the phase angle. I showed you the block sphere, but if you imagine the vector in that space, right, it will have an angle and it will have a magnitude. So there is an aspect of phase which is very important into quantum computing, and you can actually tackle these qubits through the phase operations, and we have to, because that's what gives the power to us in the computing space. And then there are other gates, like I said, poly X, which is a NOT gate. There is a Z gate which does the relative phase. Then there is Y gate that also flips as well as changes the phase, so does both NOT and phase shift at together, basically. So there are many gates, actually. The most important gates, of course, are CNOT and Hadamard gate, because if you go back to the principles and the properties of quantum mechanics, and Hadamard puts it into superposition. When a qubit is in, let's say, 0 state, right? If you run it through a Hadamard gate, it will be in a superposition of multiple states at the same time, right? And then C naught is the gate that helps you to entangle. It helps us to entangle two qubits. Now, Hadamard could be on a single gate. Some of the other gates I talked about are single qubit gates, but C naught, if you think, is like it needs to, we need to entangle two qubits, right? So it needs to be at least double qubit gate. And this is one of the simple representation of the quantum teleportation circuit. We're not going to go into details of it. It will take us just a couple of hours to go through the circuit, right? But you can see how the Hadamard gate and the C naught gates are used, and the arrow with the half, like, the arrow box in between is actually a measurement. It shows measurement, and then you can see X and Z gates as well. So typically that's how the circuit looks like. So it's, you have to prepare the circuit, then you have to kind of put it into the phase, these phases through using multiple of these gates, and then you have to measure at the end. So that's typically at a very, very, like 1,000 feet level, we do with the circuits, basically. Um, when you think about these qubits, right? Now, if you think about the hardware side of the qubits, in the classical world, we create chips, and we know semiconductors, we use those to create these chips, right? And the processors and whatnot. So in the quantum world, we have multiple different ways and we can create the hardware, right? So we have silicon photonics, which uses properties of light and photons to encode quantum information. The method is fast and it works well, and it's aligned to the silicon industry that we have as well. But there are challenges in each of this methodology, right? And that's why you see so many and so many people are still researching into all these different areas, because there are pros and cons with each of this approach, right? Then there is superconducting, which is very popular. It utilizes superconducting circuits and microwave photons, basically. It's a scalable approach, but again, it's very sensitive to noise and limited coherence times, etc., right? So um, like I said, there are multiple different approaches. Trapped ions is another famous one, which is electromagnetic fields to trap and manipulate individual ions. Um, uh, yeah, it can give us high fidelity operations and excellent qubit connectivity as well. When I say high fidelity means maintaining the quantum state. We want to maintain the quantum state for a longer time because we want to harness the quantum processing power, right? So whenever I say high fidelity, it is maintaining that quantum state for the time that we want, longer time, right? So topological is another example. Topological is said to be one approach which will get us to the fault tolerant quantum computer or industrial scale quantum computer. And I'm going to talk about it because that's where Microsoft is, and we are researching for last 18 years and invested into as well. So there are multiple approaches, right? We still have to come to the terms of, kind of consolidating on one, and we won't for some time
Deepa,
because, yeah,
may I for a moment interrupt you? There was a question on the
sure.
previous slide, the
Which
one
one
with the
was it?
circuits, with the Hadamard circuit.
Oh, yeah, yeah,
If you can go one more back,
yeah.
exactly that one. So the question was whether when we measure in between those circuits, does the result change?
Yes. I mean, as soon as you measure, you actually, so this side of circuit, sorry, my pointer isn't working, so I can't show you for whatever reason on Zoom, it isn't working. So, okay, I don't know what happened there. So, uh, right. So if you look at this circuit is all about the quantum teleportation. So you're sending the state from one place to other place, basically. And we use actually classical circuits, classical channel to do that as well. So we are sending classical bits. In quantum teleportation, when the half before measurement, that is happening somewhere else. It's Alice that is actually doing those operations. On the right hand side, it's Bob that is actually receiving the information, and he or she is doing some operations, right? Now, they both have entangled some qubits in past, right? Before that. Now, the one that is happening on the right hand side, you measure, Alice is measuring at this point in time, and she's sending two classical bits to Bob. And Bob is then using the entangled state that he has and does operations that you see here. He either does he either depending upon what he sees, he does the operation, different types of operations. He would either use I gate or X gate or Z gate or Y gate to decode the information. So yes, whoever asked that question is right. We are collapsing the state on the Alice's side at that point to send the classical information over to Bob, who would then again do some quantum operations. Yeah,
Thank you very much. I think
sure.
that's clear.
Yeah, sure. No worries. So now, if I get to the error part, right? We're not going to go into details of error. I just want to ground the fact that this all is happening at subatomic level. And at that level, these particles are absolutely like newborn babies, susceptible to anything and everything, susceptible to temperature, to frequency, entropy, anything that's happening at that level is building noise into the system. And when I say noise means they're either giving inconsistent results, or we are even getting to a point where the state is dropping, right? There's too much of entanglement in the space as well. Electrons are getting entangled continuously. So I think the whole space is very, very chaotic. And that's why if you see, even after being researching for such a long time, I talked about what 1800s and mid 18, and I think Louis de Broglie was 1924, if I'm not wrong. So it's been 100 years right now. Um, uh, we haven't been able to see any practical application of quantum computers for this very reason, because of the noisiness. To do anything practical, we need consistent results. we need reliable results, right? And we are unable to do that with the current quantum computers, which are called as noisy intermediate scale quantum computers, right? Because there's a lot of noise in the space. The error rates are very, very high if you see. Right, the number of as you increase the number of qubits, and the noise increases because, of course, they are talking to each other. They are continuously, chatting with each other, so noise increases basically. And that's why you see the chandeliers, right? You see a quantum computer, whenever you see a quantum computer, a quantum device, you see a chandelier, a beautiful golden chandelier. The chip is very small at the bottom. The whole chandelier is just to kind of keep it in vacuum at very, very low temperature, right? Temperatures lower than the outer space. That's how much we have to kind of get it to cool down and in the vacuum, right? That's when we are able to harness something out of these systems, and we are able to kind of maintain the quantum state. Again, there's cryogenic systems. There's lots that go on the hardware side on this, and we are not going to go into details of it because it could take us very, very long time. Now, if we think about quantum, like classical world and the quantum computing world, uh, then, like in the classical world, we see as soon as we started working on the hardware, right, and we got to a certain level, we started looking at the algorithms, because algorithm space is very, very important for us to take that hardware into reality, right? We need algorithms to actually map to our business problems, right? That's what we eventually want to do. We just don't want to build these computers to do nothing, basically. We want to take them into the practical world, and we need algorithms that can help us to do that. These are some examples of very foundational algorithms. There are many in the space. You go out, there are thousands, right? But these are very foundational ones. And like Dwight Georgia, it kind of is one of the early examples that proves the quantum speed up, right, over the classical algorithms. And this is basically about balanced and constant function. Um, it's very easy to say balanced and constant, but there's so much of underlying math that goes behind this, right? There's too much in terms of math that needs to be understood at the algorithm level to build these algorithms. It seems like a very small algorithm, but the math is quite important to kind of take it into at that circuit level, basically. So this algorithm, basically, when you depict it into a circuit, it actually shows us the speed up, which means if you have a balance or a constant in the classical world, it will take us to if it will take us two turns to tell us whether it's a balance or a constant function. In the classical world, we can do it with just one single operation. Now, that's the beauty of Deutsch-Georgia algorithm, and that's what it shows. Whereas there are other algorithms like Grover's search. Grover's search shows us the quadratic speed up when we are searching unstructured data within, like data within unstructured database, basically. So though that quadratic speed up actually helps us to understand, how we can break actually symmetric cryptography, to be honest, can be broken using Grover's search algorithm, but it shows the quadratic speed up on top of the classical world. That's why the cryptographic space that we can't break today, we can break with quantum once we have enough compute, because Grover's shows us how to break symmetric algorithm, whereas Shor's algorithm, which is about efficiently factoring large numbers into primes, basically, which is impossible classically, right? It's going to take us millions of years to do that classically. It gives us exponential speed up actually to do that. And Shor's algorithm tells us that we can break asymmetric cryptography like RSA, because that's what it is based on, right? It is based upon classical world not being able to factorize these large numbers into their primes, right? Whereas variational quantum algorithms are slightly newer, but they actually tell us the combination of classical and quantum world together. We are not going to be doing anything just with quantum compute for various reasons, because it is inefficient. We don't want it to do arithmetic, right? It is inefficient to do that. We want it to do certain type of problems, right? Classical world is very good at efficiently solving some problems that we do today, right? And we want to stick to that because it's very efficient and it's very cheaper as well. Because when you go in the outer world, when I work with my customers, they want ROI, which means quantum compute is very, very expensive, and it will be very, very expensive, right? So we don't want to do things which we can do classically efficiently with with classical compute, right? That's where some of the variational quantum algorithms, like variational quantum eigensolver, are very important. Are very important. There are some algorithms in the quantum machine learning space as well, like QAOA, um, uh, like and there are many more like QNN, which are also like to a certain extent classical, hybrid, basically mix of classical and quantum together. Now, there is lots that I've spoken. I would like to take a pause and see if there are questions because we are getting into now the Microsoft side of the story.
Yeah, there was another question regarding error correction. The question is, can dropping the temperature help in reducing the noise?
Yes, it does. So that's the reason why we have the whole chandelier and the cryogenic device, because we know temperature is linked to the stability and instability of the system, right? We know about the relation between temperature and entropy, and we know it can bring noise into the system. So dropping the temperature absolutely helps us to kind of keep these dancing qubits or dancing electrons, basically, or photons, so whichever, to slightly more calmer. And it does help to a great extent. And that's why we have noisy intermediate quantum computers today, which we'll see. They can't do much, but they are good for some experimentation, right? But we have them because we have been able to drop that temperature to a very, very low level, which is lower than the outer space, basically. But still, it's not enough, right? It's still not enough. Just dropping temperature is not enough. We need far more than that. We need error correction to a level where we can virtualize some of these qubits together into logical qubits. And I'll talk about that. And that's what the Microsoft's vision is all about as well. So I'll talk about that on the vision slide here.
Another question was whether quantum computers are very fast at very special tasks or at all
Yeah.
tasks.
Yeah, and that's what we are going to get into. So brilliant question. We don't want to do everything with quantum computers. When we started off, right, with in 19 mid nine like 1928, right, everything was supposed to be done with quantum. Uh, can be done with the quantum. We don't want to do everything with the quantum, and that's what most of the community has drilled down to, right? There are certain places where quantum is going to bring us value, and there are going to be certain places where it's not. So today's quantum computers are not meant for large data, the small data input, small data output, because they can't cope too much. And even going forward, we don't want to push too much data into it. So if somebody tells you large data, quantum is a good solution, no, it's not. Small data accuracy, speed up is what we are looking at with the quantum computers, basically. So this graph very nicely depicts, practical quantum advantage. And practical quantum advantage is basically the point where we start doing something that we can't do with the classical world. It's as simple as that, like it's something we can't do today, basically. So the tipping point is the crossover point is this, right? I mean, sorry, I don't have my, I don't think you can see my laser, laser point. Yeah, you can. Oh, brilliant. It's working. Can you? Can you see the laser point?
Yes,
Yeah,
yes.
okay, brilliant, brilliant. I couldn't get it working before. Some magic did happen there. So yeah, so this is a tipping point. If you see the classical world, as problem size increases, the complexity increases, the time increases, and exponentially increases, right? With quantum, it is quite linear as a graph, right? And this is a tipping point crossover. And this can be reduced further with some classical means, right? We have AI, we have machine learning, we have generative AI now. So this, again, when to start using quantum is also like, is like going up and up, actually, that crossover time, because we don't want to use it for no reason, right? So there are classical means through which we can approximate to good enough level, right? And again, there are examples. I don't know how much of you know chemistry, but I can give you example of chemistry, right? In chemistry, there is something called as active gas space. Now that space, like I don't know how many of you have seen Jacob's ladder, but Jacob's ladder basically talks about how, like, what type of like how exponentially the computer increases depending upon the active gas space. Now, active gas space means number of electrons in the chemistry. When we think about chemistry, it's molecules and it's atoms interacting to make molecules, right? So how many entangled electrons? the number of electrons increase, the gas space increase, the active gas space increases. And when the number of electrons goes beyond certain limit, we can't use classical means. That's where quantum is needed. Now we have reduced that as well. We have said we will use DFT, density functional theory, or we will use some other means, right? And like even AI and machine learning means to kind of reduce and optimize that space as well. But beyond certain limit, even those can't be helpful, right? So even DFT can't be helpful, and we still need quantum in that space. We have got many versions of DFT as well now. I'm not sure how many of you have heard, but there's deep learning DFT version as well, which Microsoft Research has come up with. That again, reduces the need for us to use quantum for some of the wider active spaces as well. And active spaces, how many electrons are getting entangled, right? So if there's more than 20 to 25, we can't do it classically today, but there are some classical means through which we can optimize that space as well to certain extent. So yes, there are some niche areas where we want to put quantum to use, not to everything, because it's not going to be of any value to us to do that. A, because it's not going to be as efficient. B, it's going to be very, very expensive to do that. And that's why algorithm space is very important. It's one of the spaces where the research has to like more research has to happen basically, because algorithms are very, very important. They give us understanding of how much quantum resources, first of all, why, and then how much, and how can we do that, the hybrid play.
Another question was whether the noise comes only from temperature or whether it is not also coming from measurement problems.
Yes, so noise is coming from multiple places, right? It's not just, and that is the exact reason why just dropping temperature is not enough. It's not enough. We have to apply other means, like quantum error correction. It's a vertical in itself, right? There's a lot of research going on in that space. It's a vertical in itself. Which actually just concentrates on error correction techniques, because no matter how much you drop the temperature, we still have noise, and noise is going to be there. I mean, it's reduced because of the reduced temperature, uh, but it's not reduced to a level where we can actually harness reliability out of the system, basically. So yes, you're right. It's not just temperature, it's many other things at play as well at that level.
Okay, so these are so far all questions I had. Now I think we can proceed.
Sure, sounds good. So quantum computers, like I said, will excel at some small data problems with super polynomial speedups, and they lie majorly at specifically simulating chemical interactions and materials. So it's majorly into material science, chemistry, where we see the first application of quantum, like creating better batteries, cleaner water, designing better drugs, quicker drugs, along with AI and HPC and new materials. Right, that's where we see quantum being used first, actually, the first application of quantum. Now, coming to Microsoft's vision, right? Um, I'm just going to look at time because I know we have only a certain amount of time. How much more do we have, Dr. Franz? Yeah.
We have about 40 minutes more.
Right. Yeah. Okay. Good. So our path of to quantum scale, with quantum scale, like scaling quantum computing to a level where it can be used for any industrial advantage, right? Is this. And this we have grounded ourselves like few years ago, saying that we don't want to do everything. Like there's too much happening in the quantum space. We want to do something that is impactful and real and can bring value uh, now or in near future, as opposed to thinking about 50 years down the line, right? So of course, we know that nothing can happen without the hardware. Anything else is useless without the hardware. So hardware is very, very important. So there's a lot of research going on in the hardware, on the hardware side to create high fidelity qubits, right? That's what we need. We need qubits which are maintaining the quantum state for a longer time, are less noisy, are reliable, basically. And there are two avenues on that side that Microsoft has been invested in. We have never, we do like our belief in the NISQ, um, like the noisy intermediate qubits is slightly less. So we have always been invested into building error correction frameworks and in topological qubits. So two avenues, logical qubits using some other hardware, right? Either neutral atom which I didn't talk about before, but neutral atom is another type of hardware, right? Where we use actually neutral atoms, as it says, cool atoms actually, cool atoms to put them into the quantum state to create qubits basically. The neutral atoms, atom hardware, putting a virtualization layer on top of it, or trapped ion. We have put a virtualization layer on top of it as well to create logical qubits, and they have given us good results. And the other avenue is the physical qubits themselves have to be better. That's where topological qubits come into picture. So I'm going to talk about those two, but there are two avenues that we have invested, and we are investing into from the hardware perspective, logical qubits using non-topological hardware, and our primary research in hardware, which is topological qubit, which is where Majorana one comes from. Then the platform, which is, we do, like I said, the idea is not to get people to do just quantum and just use quantum compute. The idea is to get people to the purpose-built platform, right, which is integrated with classical means as well, like HPC to run your AI models, AI itself, AI models and machine learning models, and the quantum compute to run the quantum routines, basically. So all together is what our vision is, to build that platform. And I'll talk about that platform. There's one slide where I can take you through that. And then quantum applications. Like I said, I've been saying right from the beginning, for us, the first application that we see is going to be into chemical materials and drug discovery science, and we are heavily invested into that. We have a first version of that application already in private preview. Satya announced it during our latest conference called as Build, which is for developers. We announced that platform as well. So that's our first. I'm not saying other industries are not going to get the value of quantum computing. They are, but we are invested to build a first pre-built platform with chemistry, material science, and drug discovery, because we see the acceleration that we can bring on that side. See, for us as Microsoft, it is not just about building some application. It is about building something which can impact everybody, which can impact every human. We want to empower every person on earth, right? And that's our motto. And that's why we have chosen this application as our first pre-built application in the AI and the quantum space. Then comes post-quantum cryptography. Like I've been saying over and over again, that the current cryptographic methods can be broken. And this is another very important research area, right? Because once I'm talking about all this, like good things we are doing on the hardware side, but it also poses threat, right, for us in the classical world, because the current algorithms, cryptographic algorithms, can be broken if we have enough compute through Shors and through Grovers, as I said. Grovers is symmetric cryptography is not that big a risk, because we have time to get there. But with asymmetric cryptography like RSA, ECC, we have a risk there through Shor's algorithm, basically. So there's immense research going on in this space, and Microsoft has been invested for the last 6 to 7 years, working with consortiums, working with different governments like US governments, NIST consortium, and many other players, academia as well, to actually create algorithms which are uh, quantum resistant, is how I would put them. And that has nothing to do with quantum as such, but because quantum is the classical means, more grounded in mathematics, to build uh, algorithms which are resistant to quantum, basically, and the threat it possesses. Now, yeah, that's like a stream in itself, and it's going to take us a long time to talk about it, because there are various different means through which we can do that, like lattice-based algorithms, there are hash-based algorithms, there are many different ones which are grounded into certain principles, mathematical principles, basically. But they are quantum resistant, and they are already been out. There are three, and if there's time, we'll talk about those. I don't think we'll have time, but that's again something that we are talking to our customers and making sure that they're embracing post-quantum cryptography, crypto agility, to make sure that the systems are safe. And we are doing it as well on our side, because we are sitting on lot of the services for our customers, right? So we have been doing this for a very long time, making ourselves crypto agile. Crypto agile means we should be able to move in the cryptographic space, not just for quantum, but for any means, for AI reasons, for any other reasons, to be able to change our cryptographic systems very, very quickly, and the mechanisms through which we secure our systems very quickly. So that's like one very important stream. So if I have to call out two streams which are highly accelerated in Microsoft, one is the quantum computing, one the hardware one, and the post-quantum cryptography, very, very important. Now, quantum readiness, as I said, it's 100 year of quantum information and science. We have partnered with UN, and we have come up with a program called as Quantum Ready Program, which is majorly for industries to get themselves ready for quantum, as it says, like look at the impact that quantum can have on their space, both positive and negative. Um, uh, Build a strategy for quantum, look at the applications that could actually benefit from quantum. So that's kind of a program that we have run. It has just started. We have run with a couple of organizations basically so far, a couple of customers. But that's in the nutshell our strategy basically. So it's quite well grounded. It's very practical as well as future looking at the same time. Any questions on the vision before we go ahead? I'm conscious that I've been speaking a lot.
So far, no questions, no more questions.
Right. So I'll crack on with this then. You remember those 50 qubits that I talked about in the physics, like the computing, when I was talking about computing, part 50 logical qubits will give us immense power, right? They don't exist. They are like this, right? This is not reality. That there are no qubit which are beautiful and reliable. Like I said, they are very error prone. They are exactly like this. We can't expect any reliability from them. That's where logical qubits come to picture, right? They're error corrected qubits with small error rates actually, not necessarily zero error rates, but small error rates, negligible error rates, rates that we can control. It's anonymous, like it is very similar to what we do in the classical world. So in the classical world, I mean, we don't actually think about it now, but back then, when we were looking at like semiconductors and building processes, right? Um, Error is there in the classical world as well. We have built mechanisms to error correct, right? We know about parity bits, we know about data bits, right? We know about all that system. We don't worry about it today because we get reliable results 100% of times, right? And that's why, nobody kind of worries about it anymore. But we are not yet there with the quantum space, right? Error correction in quantum is again very similar. we Techniques are very different, to be honest. It's not similar, but the analogy is relevant here. We have many physical qubits together making logical qubits, right? So we have data qubits and we have parity qubits, like we have in the classical world. And while computing, also we correct errors. So when I talk about what we have done with our error correction piece, right, our virtualization framework, we are as soon as we see the errors while computing, we also correct them while computing. So that's the other beauty, right? So logical qubits are key because they are reliable. They give us a reliability. Um, uh, that we want actually for our computations. So these are the levels of quantum computing. So when you think about levels of quantum computing, this is the foundation level one, and this is where we are today, right? We are in the NISQ era. Level one will, the quantum advantage that we get from level one is very low depth, actually. Like I said, very early problems like looking at entangled states or looking at random circuit sampling. Nothing beyond that, to be honest, nothing practical that could be taken to the industry. But Microsoft is very much invested into level two, and we have always been. Level two will bring us quantum advantage for scientific problems such as quantum magnets or material models, etc. Right? So as soon as we hit that 50 number, now come back to the 50 number that I talked about, right? If we have 50 very highly reliable, high fidelity qubits, then we surpass the quantum advantage. Remember, I said that. So 50 logical qubits is the tipping point. It's a tipping point for us to get to quantum advantage, which is doing something which we can't do classically. Of course, between 50 and 100, we can do far more. Uh, to do anything industrial quantum advantage, we need at least 1,000 plus. 1,000 plus logical qubits is what's needed um, for for doing anything industrial scale. Sorry, I got a message and I got distracted. Apologies for that. Um, so I'm going to skip this because I know we don't have enough time. But this actually it's an experiment done for the chirality of the molecules. Actually, I'm not going to go into details of chirality, but chirality is quite important in the R&D space, even in the pharma space for that matter, when we are making medicines, right? So. What I wanted to take back from here is not the chirality of the molecules and what was done there. What I want us to take back from this is, if you look at the logical qubits are very closer to the true ground state energy of the system that we are looking at. Okay. And physical qubit gives us the results which are far inaccurate, actually. So logical qubits actually outperform physical qubits at an enormous level, right? So logical qubits are very closer to the reality. And that's what I want us to kind of take back from this slide. There's no time for us to go into details of the experiment, actually, the chirality experiment that was done with the logical qubits. Um, but, like I will, hopefully some time this week or next week, I will share some links with Dr. Franz, and he will be able to kind of share those with you. These are some papers, right, that you can have a look at if you're interested. I'm going to also skip this video because it actually talks about the same thing, which is, merging multiple physical qubits together to make a logical qubit and correcting error while computing, right? Um, so last year has been amazing for Microsoft because we have been able to progress. We, in the sense, it has been not just good for Microsoft, but it has been good for the community as well because we have been able to show the progress, um, uh, like from 4 logical qubits to 12 to 24 logical qubits, right? Um, I remember in September when we got this result, I was at IEEE Quantum Week in Montreal, and I was very excited to see this and to read that paper because this was huge. To be honest, this both are with trapped ion with continuum hardware, um, and this one, if you look at the number of physical qubits we took, I don't have that slide here, but the number of physical qubits it took us to get to 12 is half of what we needed. Like we are tripling the logical qubits, but we are not tripling the physical qubits. The physical qubits are less than half of the triple size that we would have needed, if we would have scaled as is. But reducing number of physical qubits is very important. And it is important because we have not been able to create as many physical qubits. It's difficult, it's expensive. And as we have been hearing, right, we are not able to maintain them at certain level. We need the cryogenic device. It's not cheap. It takes a lot of energy as well. It's like from sustainability angle as well. All those cryogenic devices and all cost quite a lot, not just in terms of money, but in terms of sustainability as well. So reducing the number of qubits as we make the progress is very, very important. So this progress is not just about demonstrating more logical qubits, but it is also about reducing the number of physical qubits, right? And that is very, 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 very important. So these 24 logical qubits with neutral atom technology, with atom computing, it's a feat in itself because we were able to kind of get very higher. Um, uh, uh, like we could lower the error rates to quite a level, but also the gate fidelity was very, very good. It was 99.9% fidelity actually that we could achieve, which is quite higher than some of the other hardwares or other systems like this that you would have heard of previously. So of course it was 800 times better, but also fidelity was quite good for both single qubit as well as two qubit gates. Um,
Deepa, one
mhm.
question. Could you please explain how the step is from the physical to the logical qubit?
So from the physical to the logical qubit, actually, there is a layer in between that. So if we imagine the quantum system, right, it will start off with the hardware. It will start off with the physics and the hardware. And then we are unable to take that hardware into chip directly. We need some virtualization layer in between that does actually uh, that does actually kind of create that logical version uh, of the physical world, basically, and also which will before the software comes into picture, it should be able to give the compute to the software that is actually error corrected, but also correcting while computing at the same time, because this is not like physical world, that it's not like classical world, right? We are constantly getting errors while computation. So that whole virtualization framework that we have with Microsoft is actually doing that. So it's a layer between many layers. And I say software, but even before software, there are interpretation layers and many more, like compiler layers and many more before it hits the software layer, basically. So there are many layers. But even after hardware, this is like a virtualization layer in between, basically, to kind of do that. And there are various different techniques. There are surface codes, right, that are used in quantum error correction. I'm trying to put it in words, right? I'm trying, like, without getting into too much details because we don't have time to do that. There are surface codes that it's a technique to basically create the error, do the error correction. We have used tesseract code here, right? So tesseract codes are basically used in this case to reduce that error and map multiple physical qubits to logical qubits, and other techniques to actually correct error while computing at the same time. There are some papers, and I can share those papers actually with you, and we can go through the details. There isn't a paper that talks to exactly how Microsoft does it, but I think those papers are will actually give you a good idea about the codes and the mathematics behind it.
Okay, so and do I understand that right, that entangling also helps in error correction? Is this also a measure for getting more error-free qubits?
So entanglement is, yes, is one of the criterias, because when we're talking about two gates, right? And see, we're not going to stay in single gate. We need more and more gates, right? We have to build more and more gates because we have to entangle and superposition more qubits, right? So when we talk about um, results out of these systems, right? We always talk about fidelity and the entanglement side of it as well, right? So results will also tell you, like, how many entangled qubits were there and how we were able to preserve the entangled state for how long, and how long it could stay um, non-erroneous, basically. Or we could, like, we could actually correct the errors while computing, basically. So when you look at that paper, some of these details, including entanglement, will be part of it.
And just to have an order of magnitude, behind those four logical qubits, how many physical qubits there are?
I think if I remember correctly, I think there were 36 that were needed
Mhm.
to create four. And I remember when I saw 12, right, we used 56 to create 12.
Okay. Mhm.
So if you see idle in the, if you do the, if it is regular math, right? Four were achieved to 36 or 30. I don't remember. It was 30 or 30, 36. I mean, just maybe consider 30. To create 12, 3 times 30, 90 should have been needed, or 36 times 3. I don't know what is that. 108 should have been needed, but we did it in half, less than half.
Oh,
Yeah, it was 36. We did it in less than half, which is 56, if I remember correctly.
okay, thank you.
Yeah, sure, sure, no worries. Um, so yeah, I mean, what I want us to take home from this slide is there are many. Looking at the current hardwares, apart from topological, you would see we need many physical qubits to even get to something like this. 50 is quite possible. Microsoft has said that in next year or so, we will be able to get to 50 logical qubits, which means we will be able to get to quantum advantage. There's no doubt about that because we already have. We, in the sense, atom computing already has more than 100K good physical qubits with them. So it's just a matter of tweaking our virtualization layer to get to 50. So that is in progress, and hopefully we should see that in near term. But to get to 100, you see, we need 10K plus, quite a lot actually. We haven't seen those many, but also, but still possible, right? Because we have 200 to 2K, 3K. We see these physical qubits, so we might be able to get to 10K soon enough, or maybe in some time. We, in the sense that the hardware providers. But if you see 1000K, right, 1000 plus logical qubits that we need for anything industrial scale, that is 100K physical qubits. Now, none of us know actually, like have seen those many physical qubits, to be honest. So why do we need so many? Is because we need to create those logical qubits, right? Now, there are only two ways of achieving this. One is to build error correction techniques such that they need less and less physical qubits, or intrinsically have a qubit that is error resistant, right? Or both together. Now that's where Microsoft is invested into topological to have that both together, right? Which means a qubit that has intrinsic error correction property and a virtualization error correction virtualization layer that needs less and less. The surface code that needs less and less physical qubits to create logical qubit and to correct while computing. So this is the formula to get to the industrial scale quantum computing, right? And that's what Microsoft is heading towards. That's where you might have heard about Majorana 1, right? Which is our chip that I think it's been a couple of months now, if I'm not wrong. I saw it last month and it was amazing to see and hold the chip. There was a conference here and I was representing Microsoft, and I could actually see the chip for the first time. But what is the beauty of that chip? Why is it like so celebrated, right? In that space? Because it's small, it's fast. These qubits are small, they are fast, and they're controllable, right? What do I mean by each one of this? Why do we need small qubits? The reason we need small qubits is because on one single chip, if we can't fit enough qubits that could run enough workloads, we have to connect chip to chip. Now, research-wise, we haven't been able to make, as an industry, we haven't been able to make good progress on the quantum networking side, right? So if we have to get somewhere, then we need one chip with many qubits on it. It needs to be small. And that's not what many other hardwares are, right? So our topological qubit on Majorana is very small. It's 10 microns, right? It's very, very small. It's 1/100th of the millimeter, basically. Needs to be fast. And it needs to, when I say fast, I also mean it needs to have intrinsic error um, resiliency. Okay. Um, so we can do operations quicker, right? Because more you correct, you spend time doing that. It needs to be fast. It needs to be controllable. When I say it needs to be controllable, it needs to be digitally controllable. Most of the hardware that you see today in this era are analog. We need digital controllable because that's what we understand. That's what most of our kids understand, right? We still have a lot of classical world around us, and digital control we know is very, very important. We know, right? Digitally in bits as well. We use voltages to convert analog to digital. So this should be digitally controllable. And that's what we can achieve through the Majorana and topological qubit. It's the criteria for getting to scale, right? And we have been able to achieve all of that together. Now, because there isn't much time, to be honest, left with us, I'm not going to go into details of physics here. I would love to because I love physics, but there isn't much time. So I'm going to, at a high level, try and explain topological qubit, and then we will get very quickly um, um, into the next slides, basically. So, Eton Majorana in 1939, if I remember correctly, it's 39 or 38 or 40. I'm just not very good with dates actually. I think it's 39. He actually predicted something called as Majorana fermions for the first time. And these Majorana fermions actually are quasi-particles that exist in certain materials, particularly particularly useful in topological superconductors, basically. So these materials actually have a capability uh, to create fault-tolerant qubit, intrinsic error resistant property, basically. They are also non-abelian. They have that property, and that actually makes them fault tolerant, basically. There's more deeper meaning of what not non-abelian means, etc. But actually, you can braid these particles. You can braid some of these particles together and create fermions on the side, which are quasi-particles. They're half electrons, basically, and they preserve the state. They preserve the state of the system, and that brings the error resistance basically. It's far more deeper than this, and it will take us hours to get into details of the physics. So I'm not going to do that. But just imagine that this particle has some intrinsic error correction property, and the core to that is Majorana fermions or Majorana zero modes, how we call them basically. And they are on the two sides of this topological particle, and they create a topological state. It's a different state of matter basically that they create. Now the beauty of this is we have been researching this for 18 years. Microsoft has been researching this for 18 years actually. In 1939, this particle was predicted. We realized that this particle could actually mean quite a lot to quantum computing and was looked at as one of the hardware types to research. When we started researching for many years, we couldn't actually create this particle, to be honest. It was only in 2023, the perseverance that we had, we could create the particle in the lab. In 2024, we could actually control this particle. And 2020, end of 2024, we could actually put it on the hardware. And then in 25, we came up with this chip which had multiple of these, 8 of these topological qubits actually hardwired onto the chip basically. So there's an acceleration that you can see. What I want to convey here is the acceleration that we have seen since 2023. And the research has been going on within Microsoft since 18 years, right? Or 19 years now, actually, to be honest. So there's a speed that we have picked up over last couple of years in the research of topological qubit as well. Now, there's far more physics that goes behind it. So how you create the topological phase itself, it's not a solid, liquid, or gas state. It's a different type of state which you achieve by creating a superconductor. So some conductors actually, when put at a very low temperature, can exhibit a superconductivity, like aluminum. And when you kind of put that aluminum on top of a superconductor, on a semiconductor, basically, not superconductor. Superconductor is aluminum, but if you use then the semiconductor material to actually put your superconductor on, and then take all of that to a high magnetic field and certain electrical voltages, this nanowire or this whole apparatus actually gives the topological phase on the two sides of that wire. They're called as Majorana fermion zero modes, basically Majorana zero modes. And this wire, very small qubit, actually this nanowire converts into a topological qubit. Okay, and it has error resistant property because of the braiding nature that it has. Now, like I said, they can be controlled using digital signals as well. But that's the physics, and that's the hardware side I'm going to go into because of the time. But you must have seen the topological qubit and must have heard about it. But I just wanted to give you a glimpse of why that is important, and what it brings to the table, basically, in the sense of the topoconductor. There is no roadmap that we have come up. I mean, there is a roadmap in terms of what we want to do. Of course, we want to bring more qubits. We want to bring 1 million qubits onto that chip and also put a error correction mechanism on top of it. I'm not saying there wouldn't be error correction mechanism. We will be putting an error correction mechanism on it. But that's the roadmap. We don't have a date for this. Like on the logical side, I told you, right, in next year, we hopefully will have 50 logical qubits. I'm keeping the fingers crossed. It's the planned roadmap, but on the topological side, we don't have dates, but we know where they're heading towards. It's 1 million qubits on one single chip as a single processor, basically. That's where we're heading towards. And there has been a progress made, to be honest, on that side as well. I don't know how many of you follow, but there has been a 4-dimensional geometric code. It's a breakthrough in error correction that MSR and our quantum team together have published a paper, actually. It's actually our quantum team, not the MSR team. We have published a paper that actually talks about this novel 4D geometric codes, which can drastically reduce the number of physical topological qubits needed to form a logical qubit. It's very critical for scaling to the industrial grade scale quantum computing. So I will pass on the link to that paper as well. And that's why DARPA is invested in us, right? DARPA has put their bet on us the second time for this next decade as well. They are investing and funding us to carry on this research because they see this as the means to getting to the utility scale quantum computing. There is another company that they have invested into. It's Quantum, and that's more on the photonic side. I haven't read their papers and I haven't gone to the details of their hardware apparatus and all of that, so I actually cannot comment on it. But that's the other. I mean, and of course, photonics is. I mean, of course, photonics is quite an important hardware type as well, not just because it can create good qubits, but also because on the quantum networking side, photonics is quite relevant. We have been researching along with Photonics Inc. from Canada on the quantum internet and on the quantum networking side as well through their photonics hardware. So of course, photonics is another hardware which is to be watched out, to be watching for basically along with the topological for utility scale quantum computing. But I think this is the last slide that I'm going to take you all through because I'm conscious that we don't have more time. But this is the compute platform, right, of the future, where you would have AI, you would have HPC, and you would have quantum together. So if you see, there will be developer tools at the top. There will be hardware, multiple different types of hardwares, right? Because we are still in the era where these hardwares are built differently, right? The gates are very different. The way they are wired up are very different exactly for the same circuit can exactly for the same problem. The circuit can look different actually for different type of hardware, right? It all depends on the type of the gates available in that circuit, universal gates and whatnot, basically. But you will have different types of hardwares. You will bring your own software or algorithms, which could be in Qiskit, could be in Q Sharp, which is our QDK. It's our SDK to write quantum code. It could be Circ. It could be any of that. You can bring your algorithm in any of the language that you want, and then run on the simulator for different hardwares or actual compute. Now, some of these are still NISQ. If you go to Azure Quantum, you can get a workspace on Azure Quantum. It's our cloud space, cloud offering basically from Microsoft, where you see NISQ offering today. There is no logical offering today. There is no topological offering today, but they will be added as soon as they become available. So logical, hopefully in the next couple of years' time, and topological, as we advance with the research on the topological side. But today you will see the simulators for some of the hardware from some of the hardware providers like IonQ, Continuum. Um, uh, I think Pascal as well, if I don't remember correctly, but you would be able to point to the simulators that they provide as well as their hardware. And in the between is where the magic happens, right? So when the logical qubits come into picture, this virtualization layer will come into picture that I've been talking about, right? The error correction virtualization layer. But far more than that, if you think about, you bring a code and you want it to run on any hardware, that it doesn't happen magically. There has to be an interpreter layer that has to be written between so your hardware, the error correction, and just think about having an interpreter layer before the layer of frameworks come. Then comes the software, right? And then comes the algorithm, basically. So this interpreter layer is something that we have written already that interprets the code to different types of hardwares, basically. So that's where the magic happens. And HPC, of course, like I said, AI for science and HPC is very, very important for us in combination with quantum. So what I'm going to do is I'm going to skip some of this and just show you one single slide before we finish. Um, this, right? So I told you about Discovery, which is our first application platform, Microsoft Discovery. It's a combination of HPC, AI, and quantum. Quantum is yet to come because we are waiting for 50 logical qubits to infuse it into the Discovery platform. But Discovery platform is agentic in nature, so it has all the good means of generative AI, traditional machine learning, and AI models, some very specific models in chemistry space, and HPC offerings like I was talking about, deep learning, DFT, right? That is also part of the platform. So all this kind of becomes a big platform for scientists to reduce the R&D cycle, right? So R&D today, takes longer time because in the wet labs, we have lot many candidates going in to actually physically build those candidates, right? That's where most of the time is. The aim of the platform, the goal of the platform is to reduce the number of candidates that go into the wet lab, right? So reduce the candidate by bringing more accuracy in the play. Now that accuracy can be brought through specific AI models, purpose-built AI models, through the scale of HPC on which those models could run, and means like accelerated DFT, accelerated chemistry, or also through quantum, right? Because quantum can bring accuracy to the space. Like you remember, I was talking about active space. When there are too many electrons, everything becomes fuzzy in the classical space. Too many entangled electrons. So quantum can actually bring accuracy to that active gas space, and that accuracy at every molecular interaction layer, if you see, if you bring accuracy and reduce the fussiness, then together we could reduce the number of candidates that go into the wet lab. And that's what this shows. This is real, right? So we did, along with PNNL, we actually researched on a new battery material, which is lower in lithium, actually, just more sustainable, better battery life as well, right? So this was done along with Pacific Northwest National Lab. And this was done in 9 months' time, right? From starting the work till synthesizing the battery material. This clock actually runs on that. Was done in 9 months. This process generally takes years, right, to do. So just with HPC and AI and some quantum classical simulations, we have been able to achieve this speed of creating this new battery material. There is another example of us in Microsoft in our data centers creating coolants for sustainability to kind of run our processes with the coolants basically. That's another research. I can send you the paper for that as well. But this was all possible because we are building this hybrid ecosystem, right? It's not just quantum, and that's what I want everybody to take home from this. Is it's not going to be just quantum. It's going to be a big hybrid play with using everything that we have learned on the classical time, all the innovations that we have done on the classical side, along with the quantum and emerging quantum field. We'll be able to do discoveries like this. So I'll stop there and I'll see if there are any questions. Okay.
Yes, thank you very much. And your predictive skills are asked. So the one question is whether you think that something like Moore's law will also apply to quantum computers, and on what time scale could that happen?
Yeah, we have seen Moore's law on classical side, right? We see it in the semiconductor world quite a lot. To be honest, I don't have answer to that question. It's a very good question. I can take back and think about it or research and ask experts here as well. But it will come at play. But today we are nowhere closer to getting to the level that we want either. So when you say Moore's law, it could the way I could relate that back to is basically the single processor chip that I talked about, right? Now, can we fit 1 million in that chip? Yes, we are predicting that we can because one qubit is 100 millimeter, right? So we are predicting that in that space we should be able to put million, but it's not just qubits, right? It's all-to-all connectivity between the qubits. It's the gates that go between them as well. So there's a lot. We it's the North Star that we want to go to, right? Get to, right? Can we get to it or not? We'll have, time is the biggest answer to something like that. So we'll have to wait and watch. Yeah.
Okay, thank you. I would be interested in how the interface to the Majorana chip is. Is it wired? Is it electrical? Is it optical? How do we interact with it?
I mean, today, as far as I know, it's wired, and I could be wrong. I have not gone through to the side of where we are actually um, because it is not yet integrated into our application or into Azure Quantum for that matter. There is work going on by our teams which are working on that to get all that integrated. But for now, as far as I know, it must be wired, but I can get back to you on that question basically. I don't know whether it is optical or whether it is wired. Yeah.